Hi all. Today we will go over the quiz one review, and the purpose of this one is to understand the answer for the quiz, to clarify the answer for the quiz. Let's take a look at the quiz one statistics first. As I targeted like that, I wish most of students get the 100% or 90% score from the quiz one, and then like that. Thank you for meeting my expectation. You did a great job for the quiz one. And then let's go over each questions. So the question one is about the real mode segmentation. Uh, and then the question says this is the first instruction of JOS, and then the second instruction of the JOS is this one. And then because this long jump will change the CS register value to this one, F000. So we can assume that the CS register value is 0xF000, and then here the CS register, and then the instruction is comparing 0 to the value in the memory pointed by this address. So this is why then what is the address that this instruction read the data from? So it tries to read the data stored at the CS column 0x6AC8 to the value 0. Then what we are curious is about the address, the exact address pointed by this address by the segment and an offset pair. So that's why I mentioned about the address is equivalent to the 0xF000 colon 0x6AC8, but we know that how to calculate the address with this segment and then offset pair. That's very simple. Segment multiply by 16 and then add the offset. And because we are a computer scientist, we don't have to calculate this by hand. So we can use Python F000 multiply by 16 and then add the offset, then we can get the answer F6AC8. And then from the selections, we can see that the correct answer at here. And then 99% of the students, 195 out of 197, got the answer correctly. Next one is also for the real mode segmentation and A20. And then what's important here is that to check either whether the A20 is enabled or disabled. And let's take a look at the question. In the real mode of x86 with A20 disabled, so we should ignore the address bit at 20. Which address does the following segment offset combination points to? So F500, F300. Then let's calculate about that. So the A20 is disabled. That means we should ignore the address bit at 20. And then that means that we will regard whether or not the value of the address bit at 20th bit is 1 or 0, we will regard that as 0. So this is why we need to enable A20 if it is disabled by BIOS, because it will completely ignore all the odd addresses pointed by the address bit at 20, because we will always regard that as 0. Then let's calculate the address first. F500 multiplied by 16 plus offset F300. So that's F5000. So we have another 0, additional 0 at the end. Is multiplied by 16 to the hexadecimal number. It's just adding 0. This is simple. And then we can also use Python to calculate the exact address. So change this calculation to the hexadecimal number, then we could get the 104300. And then we should ignore bit at position at 20th bit in this number. And then because the A20 is disabled, so we will regard this one as 0. So thereby, the final address that we will get is 0x4300. That's the answer. And then a large portion of the students got the correct answer, but please make sure that the A20 disabled means that we will ignore the address bit at 20. So that's why we should ignore this 1, and then we should regard that as 0, as stated here. Next one is about the JOS Bootloader. Which of the following is not a job that the JOS Bootloader does? And then this slide shows that what JOS bootloader does, and then for the first two things are done by the BIOS. So BIOS is loaded at here, and then BIOS will load the bootloader at the 7C00, and after that it will transfer the execution from BIOS to bootloader. So these three things are done by the bootloader. And then let's take a look at the selection. So the first selection, which is the incorrect answer, which means that the JOS bootloader will do that. Load the JOS kernel to the physical address space, read the kernel ELF, that's the thing. Read the JOS kernel from disk, so read kernel ELF, so that's also included in the bootloader's job. Enable protected mode is here, enable A20 is here. So bootloader should enable protected mode to load the kernel at the physical memory, and then before doing that, we should enable A20 to fully utilize all the physical memory. So that's the reasoning. And then there is a choice that the JOS bootloader does not do, and then that's the enabling virtual memory. And then thank you so much for all the students got the correct answer for this question. Next is also about the JOS bootloader. The question is that the JOS bootloader loads the JOS kernel at the physical address at 1 mega, and how does JOS decide the address, this number, to load the kernel? And then here's the snippet of the code, how the JOS bootloader loads the kernel, and then it tries to load each program segment, and then read segment, the first argument is about the physical address, right? And then it fetches the physical address from the ELF header, program header, that kind of the elements. And then in our lab tutorial description page, so it describes that the bootloader uses the ELF, executable linkable format program headers. And then what this header does is like it specifies which is the code address, read and executable, that's the code area. So the code area starts from the physical address 1 mega, and then size is 0x7108. And then read, write, not executable, this is the data part of the kernel. And then kernel also uses the stack, so it also defines the stack area, but the addresses are all marked as a 0 because um, for stack, it will give the full permission to the operating systems to it's so to let me rephrase it first. So for the stack, because there's no restriction and like using a specific memory address, so it's operating system's discretion to fix any kind of address for the stack. In that case, we mark the physical address as 0. And then please recall that like that during the class I mentioned about the we are not using address 0 as a valid address because in C code we use a lot of pointer comparison to the null pointer to verify that the currently pointed item is valid or not. So we use the value 0 as a null, and then null semantically it means the invalid address. So we don't use address 0, so then we intentionally make all the address 0 is invalid. So please understand that like this says like the program code area starts from the 1 mega and then ends as a 1 mega plus 7108, and then the next right next to there's a code area data area, and then data area is uh, not overlapping with the code area because code area ends at the 107108, and then the data area is starting at the 108000, and then yeah, it's right next this is the right next page because it will use 7 pages, uh, actually 8 pages from 0 to 7, and then the right next page 108000, yeah, that will have a different permission flag, and then we know that like for a different page we can set a different page flag, and then that's how we separate out the readable writable data area from the code address. So let's examine each of the answer. So the first one, the incorrect one, the JOS bootloader can load the JOS kernel at any address, and because the bootloader will never use the address above 1 megabyte line, so we load that at 1 mega, but in the bootloader we can change it to the 2 mega or an arbitrary address. This is totally incorrect. The ELF header specifies that this binary program even for the JOS kernel. This program, kernel is also a program, will be correctly working if it is loaded at the specified address like this. So this answer is completely incorrect, so we should follow the guidelines that is defined by the ELF header of the JOS kernel. Second choice, after enabling the i386 protected mode, the JOS bootloader can access over 1 megabyte space of the physical memory. Because 1 mega is the start address of the over 1 megabyte address space, the bootloader loads the kernel to that address. This is also incorrect. So we cannot arbitrarily select the address. And then all the address information for the binary program in Linux or other systems, and even for Windows. Windows uses the different format, the so-called MZ format, so that they do have like this kind of structure. So the principle is that if there's a binary program, we should refer to their header that has the information about like how we can load the program to the physical or virtual addresses. So these are actually mentioning the virtual addresses F01000. So you will I believe like most of you identify that adding F at the top of the address is actually the JOS convention for like having a direct mapping to the physical memory. So we learned about that. That's why we have a virtual addresses like this. But at the bootloader, there's no virtual memory at all. So from the question 3, we verify that. So the job of the enabling the virtual memory is done by the kernel, not about the bootloader. So the bootloader completely ignores the virtual address and then just follow the guideline by the header for the physical addresses. And then the correct answer. The ELF header of the JOS kernel defines where its code and data should be loaded in the memory, yes. And then it's exactly at the 1 megabyte address. The JOS bootloader parses the ELF header to get that address and load the kernel at the right address. So that's the correct answer. Last one. All OS kernel must be loaded at the 1 mega. Similar to that, the bootloader is loaded at the physical address, physical address 7C00. So I believe like some of you get confused about this thing because like in the lab 1 exercises we practice that like the changing 7C00 to 6C00 or some other address, then like the JOS will fail to boot because bootloader expects that like they will be loaded at 7C00. But the kernel, they expect where it is being loaded and then that is written in here. Yeah. That's why we should follow the guideline. Then why the JOS bootloader does not have that kind of a header and then it always need to be loaded at the fixed address is that this kind of a header information takes a space. So for the usually for the ELF header, even if for the very small program, it will take around the 200 or 300 bytes for this kind of the information. But please recall that the JOS bootloader and then any other bootloader, if it is booted from the BIOS, so not from UEFI, then like we have a limited space for the bootloader, 512 bytes, but the last 2 bytes need to be fixed as a 55AA or something, so we only have 510 bytes for the loading the code. Then loading the header information around the 300 bytes, that could be too much space overhead. So that's why we don't put any kind of header to the bootloader and then just use the fixed address loading at the 7C00. But please note that doing such is a bad engineering practice. That's why we should have this kind of the ELF header and then allowing the program to be transparently used any kind of address. So we are actually practicing that in the operating system from like from the old days. But many people know that like loading the start of the bootloader at the fixed address space is not that great design. So that's why like so there are many reasons that we switched from the BIOS to the UEFI or some other advanced boot. So right now, like we are calling that the BIOS boot as a legacy boot mode because there are many new things. But having a UEFI and then like not loading the bootloader at the start release the restrictions of like having a fixed address for the bootloader loading. That's the thing. And then next is question 5 is about the x86 program stack. So this asks questions about the how you implemented JOS for the exercise 10, 11, 12 for printing the program stack for the monitor function. And then let's follow the question descriptions. Suppose you have the following code snippet in your JOS. Which will be the correct assignment to print the current base pointer, EBP, and save the return address, the EIP, to the console? So there are some part of the code, but to correctly following this kind of thing, so either following your JOS code, or you can refer to the JOS tutorial slide about like which value you need to put the printing the EBP and EIP. So here EBP and EIP, and to print that, so you need to put the result of the read EBP to the EBP printing. So the first answer need to be the read EBP, but the read EBP has already been done in here, so we just can put EBP at here. And then for EIP, so EIP is the return address, and then EBP is right at here, so EBP accessed with the index 1. So because we will regard everything as a 4-byte because it's a 32-bit, and then we define EBP as an integer form pointer, so whose data type is 4-byte. So EBP indexed by 1 is not the 1-byte here, it will jump 4-byte and then select the return address. So the return address stores it means that like a previous EIP, saved EIP. So what we need to put is like we need to put EBP to this one, and then EBP indexed by number 1 at EIP. So the correct answer is this one. Question 6 is about the protected mode segmentation. So we've practiced this for many times, and then I will just follow the address or whether the access is valid or not with this global descriptor table. So let's start with the pair A. So the segment selector is 0x10, and then the offset is 10010. So to calculate the address, we need to follow the selector first, so 0x10, and then we should fetch the base address, and then add the offset. So if we add these two numbers, so 1 and 1, so it'll become 2, and then rest of the things are all 0, so 1111, 2010. That is the address. But not so we should also compare whether the current offset is within the limit. So the limit value is a 1000 in hexadecimal, which is 4096, but we should honor the G flag to calculate calculate the exact limit, because the granularity of the limit is 1 page if G is 1. So the actual limit is like this value multiplied by this page size. So actually the limit is 16 megabyte region. So it's quite huge. So the offset is just a 4 kilobyte plus 10. So that's allowed. So this is all okay. So the resulting address is this one. And then the last step is to check the privilege. So the data privilege level of this descriptor is 0. That means only ring 0 can access that. And then to get the current privilege level, we should take a look at the segment selector. So for the segment selector, this is 16, and then if we change this as a binary number, then 10000, that is a 16. And then last 2 bits stores the current privilege level. These are 0, so we are in ring 0, so we can access data privilege level 0. And then for those who like they get confused about like where to store the current privilege level is at the end of each segment selectors. And then for the segment selector values, so we will never use the last 3 digits of the binary digits of the segment selector because like this kind of the descriptor will be 8-byte aligned. So that means the last 3 digits in binary number is 0. Yeah. So that means that we should take a look at the last 2 bits. So for 8, that's the current privilege level 0. For 0x13, then the current privilege level is 3. So 0x10, then current privilege level is 0, something like that. So we can easily get the current privilege level from the last 2 digits in the binary for the segment selectors. So we handled the first one, and then let's move on to the second one. So 0x8, and then the offset is 0x999. So we will choose the second segment, so 0x pointed by the selector 0x8, and then take the base address, then add the offset, and then resulting address is this one. And then we should compare the offset is within the limit, or we should check that. And then limit is 1000 hexadecimal, but the offset is like the little less that. So it's not one less, it's far less than the 1000, because the 1000 minus 1 is a FFF. Yeah. So it's within the limit, so that's okay. And then the next is about checking the current privilege level and the data privilege level. So the data privilege level is 3, but the current privilege level is 8. So this is a typo. So there should be no ending 0 here because the value is 8, but the result is the same. Last 2 digits of the bits are 0. So that means the current privilege level is in ring 0, so it can freely access DPL3. So this address is valid, and then we can access that. And then the last one, so 0x13. So when selecting the segment for the global descriptor table entry, so we should ignore the last 2 bits of the segment selector, so it will go to the first segment. And then, because we take a look at the segment first, so let's focus on the data privilege level first. So if we change this value, 0x13 is actually 19, 16 plus 3, yeah, in the hexadecimal number, 16 plus 3, so we can easily get the last 2 bits are like the 3. So that means the current privilege level is in ring 3, but the data privilege level is pointing that the only ring 0 can access that. So for this one, even if we translate the address correctly, the CPU will block the address, and then that's how protected mode works. So the correct answer for the correct choice for the C is like the invalid address. And then please recall about this kind of the privilege level diagram. So ring 0 is the most highest privileged, and then the ring 3 is the least privileged. So that's why ring 3 can read ring 0. So that's the case of B. But case of C, we are ring 3, but attempted to read the memory of the ring 0, then that's prohibited. So the correct answer is that we should choose the address for the A, correct address for the B, but for C, case of C, the access is invalid. Yeah, I can see that like some of the students chose that like a correct address value for the C, but the important thing is like we should also check the data privilege level and then current privilege level. Question 7 is about the virtual memory. We have learned the 3 goals of the virtual memory: transparency, efficiency, and protection. And then which of the following describes the transparency goal? So the goal of the transparency is about something like this. So suppose we have this example, we have only 2 programs, and then suppose you have many multiple programs are running. So it could be same program, or it could be total different program, but some naive engineering practices like they just use the default addresses for like creating some of the programs. So in 32-bit Linux, so one of the tradition right now is like changed, but one of the practice about the 32-bit Linux programs are their code will always starting at the address 0x80480000. So if you just take some of the source code and then compile it in like the 10-year ago Linux system or something, all the program will be starting at this address. But from the example of like Ogni with the physical memory, if one of the program took this address, then the second program cannot take the same address in physical memory because physical memory is a limited resource, and then like the cannot be shared like that. So the problem was like if we loaded this program first and then the second program as next, then the second program need to be aware about the system state about whether in the same address the other program has been loaded or not. So in that case, the second program's choice need to be migrating all these region to the another way, or kick out the first program and then to be loaded in the correct address. But we all know that the ELF header will define the address of each program. And then if we change the address like that, then it will never work. So that kind of the design will never work with only with the physical memory. So the transparency goal is to let the programs don't have to be worrying about like the what is the memory usage status about the system. Yeah. So in the virtual memory, we will have this kind of the instruction table per each program. So this blue table is corresponding to this first program, and then green table corresponds to the second program. And then while having the fixed address in virtual, we can have the completely orthogonal address space on the physical memory. So even if it is scattered like this, so even the code addresses are not in order, so that doesn't matter because these are virtually in order like this, while the physically it is like totally scattered. And then let's take a look at each selection, and then let's take a look at which one describes this kind of the problem at best. So the first one is that without virtual memory, a program may access code and data owned by the other programs. Virtual memory systems can prevent this by providing an isolated virtual address space to each of them. So this description is more about the protection. It's not about the transparency at all because like it's telling about the prevent isolation and that kind of the concept. And the second description is about the efficiency, physical memory may suffer from memory fragmentation, cannot utilize the entire free physical memory due to fragmentation. What that means is that even if we have a free space enough to accommodate one program, but due to the fragmentation, we could not accommodate that program without migrating existing programs. So that's about the fragmentation efficiency kind of thing. So this is not related to the transparency. But the next one is the correct answer. So all the students except one student responded correctly. And then that is about the suppose a program has been loaded to an address 80480000. And then you have another program that requires this is the same address. And then we cannot load both of them and run both programs at the same time in the physical memory space because the address is colliding. But we can load both programs at the same virtual address while having totally different physical address. And then that's the beauty of the virtual memory system for the transparency. So the answer is this one. Next one is about the same virtual memory, but about the efficiency. And then the efficiency, the problem was about the memory fragmentation. So suppose we have two programs and then the already loaded program one. Well, we have a free spaces like the 64, 96, and the 128 kilobyte, but as a sum of the all free space, that's actually bigger, the exactly same to the program second program size. But the problem is that the stack program data, program code, these kind of the reason need to be allocated contiguously per each region. We can allocate the stack and the program data because there are like the big free space enough to accommodate each of the region, but for program code for a second program. So it has a size of the 160 kilobyte, but we do not have a physical memory that is free for contiguous 160 kilobytes. So that was the problem, even if we have a free memory space. So if we move all this program one's occupied area to like the some of this shifting all the things to the down and then to be make it as a program one as a compact and contiguous, then we can load the program too, but we cannot do that on the fly. So this is about the fragmentation problem. So the correct description is that the physical memory may suffer from memory fragmentation, and then the virtual memory can resolve that by like managing all the memory and page granularity. And then the next three questions are like the address translation in like the virtual memory. And then we practiced these kind of the table walkthrough before, so like I will directly get into the answer description. So the question is about that the CR3 register points to the page directory. Then this is the corresponding page table. And then the question is that which physical address, that virtual address, this one is translated to. So let's take this address 8020567, and then we will split it with by the last three digits because we will not translating in page offset, and then we will take the top five digits. And then that's the virtual page number. and then offset, we have the offset. And then with the virtual page number, we need to split it into like the exactly 10 bits each. And then for page directory index and table index to index each entry. And then if we translate these into binary numbers, this is something like this, and then cut it exactly in the middle, then 10 bits for the page table index, 10 bits for the page directory index. So higher 10 bits are page directory index, that's the 0x20, so we will choose this entry. And then lower 10 bits are 0x20, then we will follow physical page number here, so we are referring to the page table and 444000, and then we will also use the page table index 0x20 to index the correct page table entry. So we will choose 0x20 from the page directory, follow this physical page number, so exact address is like adding 30, so that's why we should find the page table at this address, and then index the page table again with the page table index, then we will get the physical page number for the target address. So we got the physical page number as a 345, and then we have the offset in the address, just concatenate it. So the correct answer is 345,567. So that's how we can get the result like this. And then question 10 is about translating a different address. So the address is 8021,333. So let's do the same thing. Last 3 digits are offset, and then first 5 digits are virtual page number, and split it into 2, and then write it as 20 bits for the virtual page number, and then split in the middle, and then now we get the page directory index as a 0x20, page table index as a 0x21. And then we will follow the page directory by indexing with the page directory with the page directory index at 0x20. Then it says the physical page number for the corresponding page table is 111, and then the address is 111000. So we move down to the page table and then index the page table with the page table index 0x21. Then now we get the 678 as a physical page number. So the physical page number is 678, and then we just inherit the offset from the virtual address, then concatenate it. So the resulting physical address is 678,333. So the correct answer is this one. And then the last one. Last one is not about the calculating the address. So the question is that what is the memory permission applied to the virtual address? This one. Then to get the permission flags, so we need to walk down the page directory and page table. So we should do the same steps. We should take the same steps to address translation, but we will focus on the flags at this time. So write down the address like this, and then we have practiced that, and then page directory index is 0x20, and then page table index is 0x20. So we choose 0x20 at here, 111, 111000, that's the page table. Then page table index is this one, but we will focus on the permission flags. So in the page directory entry, we have PTP and PTW, these two are set. So it seems like that in the page directory entry, the operating system would like to, so the address is valid, and then like the page directory would like to give the writable permission to the memory on top of the readable permission, because PTP implicitly allows the address is valid, so like they can read it. And then let's move down to the page table entry. So page table entry, in contrast, this is valid, but in contrast, they would like to, the operating systems would like to set it as a user accessible to the user level, but the read only. But the page table, page directory entry, they are not working independently. The CPU will check the permission at the page directory at first. If this is not conform to this permission flags, the CPU will reject it. And then when we walk down the page table, if the access does not conform to these flags, then it will be rejected. So the principle is that like we should take the set intersection of the flags available in the page directory and table entries. So both need to be permissive to allow the correct permission for that. But in this case, these flags are different. Then we need to take the set intersection, and that means only the PTP. So we should regard that in this kind of the access, the only access allowed is the only enabled bit is the PTP. So the address is valid, read only, but not accessible from the user. So PTP valid. There's no PTW, so not writable. There's no PTU, so only for ring 0. So the correct answer is readable, valid, not writable, but inaccessible to user. So that's the correct answer. I hope that like you all use the time for taking the quiz and not just for like the earning the score, but revisiting all the things that we have learned for the first 4 weeks and check that whether you have know that correctly or not. And then this quiz review videos, maybe some of you are thinking that we are repeatedly doing the same thing for the 3 lecture time, but the important thing is like that by doing this, you will never forget the answers and then reasonings about how to get the answer or like how the like the some like the starting part of the operating systems are working. Thank you, and then thank you for your attention, and then we will have in-person lectures starting from next week. Let's meet on coming Tuesday.